For most of human history, we thought space was pretty simple, a big, flat stage where the events of the universe unfold. Even if you take down the set of planets and stars, there's still something left. That empty stage is space, and it exists, unchanging and eternal. Einstein's theory of relativity changed that. It says that space and time make up that stage together, and they aren't the same everywhere. The things on the stage can affect the stage itself, stretching and warping it. If the old stage was like unmoving hardwood, Einstein's stage is more like a waterbed. This kind of elastic space can be bent and maybe even torn and patched together, which could make wormholes possible. Let's see what that would look like in 2D. Our universe is like a big flat sheet. Bent in just the right way, wormholes could connect two very, very distant spots with a short bridge that you could cross almost instantaneously, enabling you to travel the universe even faster than the speed of light. So, where can we find a wormhole? Presently, only on paper. General relativity says they might be possible, but that doesn't mean they have to exist. General relativity is a mathematical theory. It's a set of equations that have many possible answers, but not all maths describes reality. But they are theoretically possible, and there are different kinds. The first kind of wormholes to be theorized were Einstein-Rosen bridges. They describe every black hole as a sort of portal to an infinite parallel universe. Let's try to picture them in 2D again. Empty space-time is flat, but curved by objects on it. If we compress that object, space-time gets more curved around it. Eventually, space-time becomes so warped that it has no choice but to collapse into a black hole. A one-way barrier forms, the event horizon, which anything can enter, but nothing can escape, trapped forever at the singularity at its core. But maybe there is no singularity here. One possibility is that the other side of the event horizon looks a bit like our universe again, but mirrored upside down, where time runs backwards. In our universe, things fall into the black hole. In the parallel universe with backwards time, the mirror black hole is spewing things out a bit like a Big Bang. This is called a white hole. Unfortunately, Einstein-Rosen bridges can't actually be crossed. It takes an infinite amount of time to cross over to the opposite universe, and they crimp shut in the middle. If you go into a black hole, you won't become the stuff coming out of the white hole. You'll only become dead. So, to travel the cosmos in the blink of an eye, humans need a different kind of wormhole, a traversable wormhole. If string theory, or one of its variations, is the correct description of our universe, then we could be lucky and our universe might even have a tangled web of countless wormholes already. Shortly after the Big Bang, quantum fluctuations in the universe at the smallest scales, far, far smaller than an atom, may have created many, many traversable wormholes. Threaded through them are strings, called cosmic strings. In the first billionth of a trillionth of a second after the Big Bang, the ends of these tiny, tiny wormholes were pulled light years apart, scattering them through the universe. If wormholes were made in the early universe, whether with cosmic strings or some other way, they could be all over, just waiting to be discovered. One might even be closer than we realize. From the outside, black holes and wormholes can look very similar, leading some physicists to suggest the supermassive black holes in the center of galaxies are actually wormholes. It will be very hard to go all the way to the center of the Milky Way to find out though, but that's okay. There might be an equally extremely hard way to get our hands on a wormhole. We could try to make one. To be traversable and useful, there are a few properties we want a wormhole to have. First, it must obviously connect two distant parts of space-time, like your bedroom and the bathroom, or Earth and Jupiter. Second, it should not contain any event horizons which would block two-way travel. Third, it should be sufficiently sized so that the gravitational forces don't kill human travelers. The biggest problem we have to solve is keeping our wormholes open. No matter how we make wormholes, gravity tries to close them. Gravity wants to pinch it closed and cut the bridge, leaving only black holes at the ends. Whether it's a traversable wormhole with both ends in ours, or a wormhole to another universe, it will try to close unless we have something propping it open. For very old string theory wormholes, that's the cosmic strings job. For man-made wormholes, we need a new ingredient: exotic matter. This isn't anything like we find on Earth or even antimatter. It's something totally new and different and exciting, with crazy properties like nothing that's ever been seen before. Exotic matter is stuff that has negative mass. Positive mass, like people and planets and everything else in the universe, is attractive because of gravity. But negative mass would be repulsive. It would push you away. This makes a kind of anti-gravity that props open our wormholes. And exotic matter must exert enormous pressure to push space-time open, greater even than the pressure at the centers of neutron stars. With exotic matter, we could weave space-time however we see fit. We may even have a candidate for this exotic matter, the vacuum of space itself. Quantum fluctuations in empty space are constantly creating pairs of particles and antiparticles, only for them to be annihilated an instant later. The vacuum of space is boiling with them, and we can already manipulate them to produce an effect similar to the negative mass we're looking for. We could use this to stabilize our wormholes. Once we're keeping it open, the ends would start together, so we'd have to move them around to interesting places. We could start by wiring the solar system, leaving one end of each wormhole in orbit around the Earth. We could fling others into deep space. The Earth could be a wormhole hub for a vast interstellar human civilization spread over light years, but only a wormhole away. However, wormholes have a dark side. Even opening a single wormhole kind of breaks the universe in fundamental ways, potentially creating time travel paradoxes and violating the causal structure of the universe. Many scientists think that this not only means they should be impossible to make, but that it's impossible for them to exist at all. So for now, we only know that wormholes exist in our hearts and on paper in the form of equations. We know you want to know more about universe stuff, so we're trying something new. Kurzgesagt and Brilliant are collaborating on a 6-part video series about our favorite science and space things. Thanks to their help, there will be more videos on this channel in the next 6 months. Kurzgesagt has worked with Brilliant for a while now, and we love what they're doing. In a nutshell, Brilliant helps you to get ahead by mastering maths and science skills through actively solving challenging and fascinating problems. To support our collaboration with them, visit brilliant.org/nutshell and sign up for free today. The first 688 people that use the link will get 20% off their annual premium subscription.
Let me introduce you to the skies. Then I'll introduce you to the ground.
There is a hole at the bottom of math. A hole that means we will never know everything with certainty. There will always be true statements that cannot be proven. Now, no one knows what those statements are exactly, but they could be something like the twin prime conjecture. Twin primes are prime numbers that are separated by just one number, like 11 and 13 or 17 and 19. And as you go up the number line, primes occur less frequently, and twin primes are rarer still. But the twin prime conjecture is that there are infinitely many twin primes. You never run out. As of right now, no one has proven this conjecture true or false.
But the crazy thing is this. We may never know. Because what has been proven is that in any system of mathematics where you can do basic arithmetic, there will always be true statements that are impossible to prove. That is life.
Specifically, this is the game of life, created in 1970 by mathematician John Conway. Sadly, he passed away in 2020 from COVID-19. Conway's game of life is played on an infinite grid of square cells, each of which is either live or dead. And there are only two rules. 1, any dead cell with exactly 3 neighbors comes to life. And 2, any living cell with less than 2 or more than 3 neighbors dies. Once you've set up the initial arrangement of cells, the 2 rules are applied to create the next generation, and then the one after that, and the one after that, and so on. It's totally automatic. Conway called it a 0-player game. But even though the rules are simple, the game itself can generate a wide variety of behavior. Some patterns are stable. Once they arise, they never change. Others oscillate back and forth in a loop. A few can travel across the grid forever, like this glider here. Many patterns just fizzle out. But a few keep growing forever. They keep generating new cells. Now, you would think that given the simple rules of the game, you could just look at any pattern and determine what will happen to it. Will it eventually reach a steady state? Or will it keep growing without limit? But it turns out this question is impossible to answer. The ultimate fate of a pattern in Conway's game of life is undecidable, meaning there is no possible algorithm that is guaranteed to answer the question in a finite amount of time. You could always just try running the pattern and see what happens. I mean, the rules of the game are a kind of algorithm after all. But that's not guaranteed to give you an answer either, because even if you run it for 1 million generations, you won't be able to say whether it'll last forever or just 2 million generations, or 1 billion, or a Googleplex. Is there something special about the game of life that makes it undecidable? Nope. There are actually a huge number of systems that are undecidable, like Wang tiles, quantum physics, airline ticketing systems, and even Magic the Gathering.
To understand how undecidability shows up in all of these places, we have to go back 150 years to a full-blown revolt in mathematics.
In 1874, Georg Cantor, a German mathematician, published a paper that launched a new branch of mathematics called set theory. A set is just a well-defined collection of things. So the 2 shoes on your feet are a set, as are all the planetariums in the world. There's a set with nothing in it, the empty set, and a set with everything in it. Now, Cantor was thinking about sets of numbers, like natural numbers, positive integers like 1, 2, 3, 4, and so on, and real numbers, which include fractions like 1/3, 5/2, and also irrational numbers like pi, e, and the square root of 2. Basically, any number that can be represented as an infinite decimal. He wondered, are there more natural numbers? Or more real numbers between 0 and 1? The answer might seem obvious. There are an infinite number of each, so both sets should be the same size. But to check this logic, Cantor imagined writing down an infinite list, matching up each natural number on one side with a real number between 0 and 1 on the other. Now, since each real number is an infinite decimal, there is no first one, so we can just write them down in any random order. The key is to make sure we get them all with no duplicates and line them up 1-to-1 with an integer. If we can do that with none left over, well, then we know that the set of natural numbers and the set of real numbers between 0 and 1 are the same size. So assume we've done that. We have a complete infinite list with each integer acting like an index number, a unique identifier for each real number on the list. Now, Cantor says, start writing down a new real number. And the way we're going to do it is by taking the first digit of the first number and adding 1. And then take the second digit of the second number and again add 1. Take the third digit of the third number, add 1. And keep doing this all the way down the list. If the digit is a 9, just roll it back to an 8. And by the end of this process, you'll have a real number between 0 and 1. But here's the thing. This number won't appear anywhere on our list. It's different from the first number in the first decimal place, different from the second number in the second decimal place, and so on down the line. It has to be different from every number on the list by at least 1 digit, the number on the diagonal. That's why this is called Cantor's diagonalization proof. It shows there must be more real numbers between 0 and 1 than there are natural numbers extending out to infinity. So not all infinities are the same size. Cantor called these countable and uncountable infinities respectively. And in fact, there are many more uncountable infinities which are even larger. Now, Cantor's work was just the latest blow to mathematics. For 2,000 years, Euclid's Elements were considered the bedrock of the discipline. But at the turn of the 19th century, Lobachevsky and Gauss discovered non-Euclidean geometries, and this prompted mathematicians to examine more closely the foundations of their field. And they did not like what they saw. The idea of a limit at the heart of calculus turned out to be poorly defined. And now Cantor was showing that infinity itself was much more complex than anyone had imagined. In all this upheaval, mathematics fractured, and a huge debate broke out among mathematicians at the end of the 1800s. On the one side were the intuitionists, who thought that Cantor's work was nonsense. They were convinced that math was a pure creation of the human mind, and that infinities like Cantor's weren't real. Henri Poincaré said that later generations will regard set theory as a disease from which one has recovered. Leopold Kronecker called Cantor a scientific charlatan and a corrupter of the youth, and he worked to keep Cantor from getting a job he wanted. On the other side were the formalists. They thought that math could be put on absolutely secure logical foundations through Cantor's set theory. The informal leader of the formalists was the German mathematician David Hilbert. Hilbert was a living legend, a hugely influential mathematician who had worked in nearly every area of mathematics. He almost beat Einstein to the punch on general relativity. He developed entirely new mathematical concepts that were crucial for quantum mechanics, and he knew that Cantor's work was brilliant. Hilbert was convinced that a more formal and rigorous system of mathematical proof based on set theory could solve all the issues that had cropped up in math over the last century. And most other mathematicians agreed with him. "No one shall expel us from the paradise that Cantor has created," Hilbert declared. But in 1901, Bertrand Russell pointed out a serious problem in Cantor's set theory. Russell knew that if sets can contain anything, they can contain other sets, or even themselves. For example, the set of all sets must contain itself, as does the set of sets with more than 5 elements in them. You could even talk about the set of all sets that contain themselves. But this leads straight to a problem. What about R, the set of all sets that don't contain themselves? If R doesn't contain itself, well, then it must contain itself. But if R does contain itself, then by definition, it must not contain itself. So R contains itself if and only if it doesn't. Russell had found another paradox of self-reference, and he later explained his paradox using a hairy analogy. Let's say there's a village populated entirely by grown men with a strange law against beards. Specifically, the law states that the village barber must shave all and only those men of the village who do not shave themselves. But the barber himself lives in the village too, of course, and he's a man, so who shaves him?
1 minute.
If he doesn't shave himself, then the barber has to shave him. But the barber can't shave himself because the barber doesn't shave anyone who shaves themselves. So the barber must shave himself if and only if he doesn't shave himself. It's a contradiction. The intuitionists rejoiced at Russell's paradox,